Throughout human history, scientists, philosophers, theologians, and others have pondered this beautiful gem called Earth, floating in the seemingly empty blackness of space. The most influential of the early Greek astronomers believed that the Earth was at the center of the universe. This view prevailed in the Western world until the 16th century, when Copernicus advanced the radical notion that the planets orbit the sun instead. Then, in the 17th century, Galileo pointed a telescope skyward to study the heavens. In his observations of the moons of Jupiter, the phases of Venus, and the craters of Earth's moon, Galileo provided startling new astronomical data that strongly supported a heliocentric or sun-centered view of the universe. Meanwhile, in Central Europe, Johannes Kepler further refined this notion by demonstrating that each planet orbits the sun in a non-circular orbit, known as an ellipse. But not until the work of Isaac Newton was the mystery of planetary motion finally unraveled with absolute mathematical certainty. In the years since then, countless scientific breakthroughs have provided still more clues about where our planet sits in the celestial scheme of things. Yet questions linger as we seek to better understand planet Earth. How exactly did this world of ours form? And why is it so different from the other known planets?
One characteristic that makes Earth unique in our solar system is life. Living things can be found virtually everywhere on Earth. High on mountain peaks, in deep ocean basins, in the hottest deserts, and at the icebound poles. Life has even been found in such seemingly inhospitable environments as active undersea volcanoes and hot, acidic sulfur springs. The presence of life clearly distinguishes Earth from its neighboring planets, but life hasn't always existed here. In fact, at the time the solar system came into being, an event we estimate to have occurred about 4.6 billion years ago, Earth was a very different planet than the one we know today.
The most widely held scientific theory of the origin of the Earth and of the entire solar system was first advanced by the German philosopher Immanuel Kant, and later by French mathematician Pierre-Simon Laplace. They held that the sun and planets condensed from a nebula. Support for this idea came with development of more powerful telescopes and spectrometers, which can detect the composition of material deep in space. Nebula are created by the explosion of stars, which have exhausted their nuclear fuel. By studying the compositions of nebula, astronomers have found evidence that stars and planets can form from these interstellar clouds. 99% of nebular material is composed of hydrogen and helium gas. But about 1% consists of tiny bits of solid matter, silicon compounds, iron oxides, carbon, and a host of other materials, all of which are found in the sun and planets. If the force of gravity between the gas and bits of cosmic dust is strong enough, this matter is gradually pulled together. As the nebula contracts, it starts spinning, with heat setting its particles in motion. The further it condenses, the faster it rotates. The process is something like what happens when a skater condenses himself by drawing in his arms until his body becomes a blur. Gradually, the gas and stardust become more and more concentrated at the center of the nebula, heating up to form a star. The material spinning around a new star flattens into a disk, drawn there by gravity from the equatorial bulge created by the star's rotation. Over tens of millions of years, dust gathers as clumps in the hot disk. These collide and weld together under the influence of gravity, forming larger objects called planetesimals, which in turn come together to form the planets. The precise details of this accretionary process remain unclear. Ultimately, the gases themselves partially crystallize and condense to form balls of ice.
The cloud of material from which the planets formed started out as being mostly gas with a small amount of dust. That dust was very fine indeed. But the particles collided with each other, and during those collisions, they stuck with each other so that material started to coagulate into still bigger bodies. So you have to imagine that we went from dust particles all the way up to objects that were kilometers across. Those objects were colliding with each other, making still bigger bodies, so that we think of the formation of solid planets like the Earth as being a hierarchical process, a process that starts off with very small things, very large in number, towards intermediate-sized things, smaller in number, and eventually ending up with a very small number of large objects. As an intermediate stage in this process, we could imagine that the region where the Earth formed contained hundreds of objects that were about the size of the Earth's moon. Most of those objects then coalesced to make a single planet, the Earth.
The most ancient landscapes in our solar system still bear the scars caused by the violent impact of these objects as they were swept up by the orbiting planets. Indeed, impact craters are a dominant feature on the surface of most bodies in the solar system. When meteorites slam into our planet, they travel at speeds between 11 and 70 kilometers per second. Virtually in an instant, the underlying crust can be shattered to a depth of several kilometers and heated to temperatures as high as 15,000 degrees. The resulting material is a mix of pulverized debris and black melted rock fragments. This Canadian crater, seen from space, is over 60 kilometers across. Lakes fill the troughs near its rim. But unlike the rest of the planets, erosion and sedimentation have removed the craters of most impact sites on Earth. Other important differences exist between the planets as well, and these also provide clues about the formation of the solar system. The 9 planets differ greatly in appearance. From gas giants like Jupiter and Saturn to the much smaller terrestrial or rock planets such as Venus and Mars. The nebular hypothesis provides an explanation for this diversity.
Planets have a variety of compositions, chemical makeups, and we think that came about because when the solar system formed, there was a range of temperatures, from very high temperatures close into the sun to much lower temperatures further out. The main difference in the solar system is between the planets which are Earth-like, by which we mean Mercury, Venus, Earth, and Mars, and the more distant planets, Jupiter, Saturn, Uranus, Neptune, and Pluto. These more distant planets are rich in ice and gas. The ice in particular is material that would not be able to condense close into the sun in the region where the Earth formed. So to a first approximation, the dominant difference within our solar system lies between the Earth-like planets and the more distant planets, and this in turn is related to the gradual decline in temperature as you go outward from the sun.
In addition to the 9 familiar planets, between Mars and Jupiter there lies a belt of drifting rubble, the asteroids. Fragments of rock are set free by collisions among these asteroids. This is the source of most of the meteorites which strike Earth in present geological time. These rocks from the asteroid belt are over 4.5 billion years old. They are typically rich in silica, alumina, iron, and nickel. Such elements are common inside the Earth. The overall density of the Earth is also close to the average density of meteoritic material. So it seems likely that meteorites represent the same type of raw material which accreted to form the Earth. But rocks forming the outermost layer of Earth today are much different in composition from that of many meteorites. For example, a common continental rock is granite, which is lighter in weight than meteoritic material. This suggests that this planet must have originally had a very different structure than it does today. Scientists believe that initially it was a homogeneous blob of silicon compounds, iron, magnesium oxides, and lesser amounts of all the other natural chemical elements.
Understanding how Earth was transformed from a homogeneous mass to a planet with distinct internal layers is fundamental to understanding Earth history. This process, known as differentiation, is responsible for dramatic changes in Earth's physical identity since the formation of our planet some 4.6 billion years ago. These changes include volcanic activity, the formation of continents, the ocean and atmosphere, and even initiation of the Earth's magnetic field. The event which triggered the differentiation process was a dramatic heating of the Earth early in its history. Several factors may have contributed to this heating, but the most important was the presence of radioactive elements in the rocks of primitive Earth. As these elements decayed, their atoms emitted vast quantities of energy, which was rapidly converted into heat. As the temperature of the Earth rose, the rocks began to soften and partially melt. While it's unlikely that the Earth became entirely molten, the heating and melting allowed the rocks to flow and change position or differentiate according to density. The lightest material floated to the surface, forming a scum or crust on the Earth. Denser rock and magma sank, concentrating the heaviest material in the Earth's core.
The young Earth was an irregularly shaped ball of rock adrift in space. As meteorites were pulled into the planet by gravity, it grew larger and gradually acquired a spherical shape. At the same time, a layered structure began to evolve. No one knows how long it took for Earth to differentiate into its present structure. Some of the oldest known terrestrial rocks resemble rock types forming today, suggesting that Earth's layering had begun to develop within the first 500 million years of the planet's history. Geophysicists have developed a remarkably clear picture of Earth's interior.
At the very center of the Earth, we have a solid inner core, which is frozen iron. It's about the size of the moon. It's a crystalline ball just floating at the center of the Earth. Outside of that is the molten outer core. This is liquid iron, very low viscosity. And as I mentioned, the inner core is just floating inside this molten iron ball. Then as we get to about half the radius of the Earth, we enter the solid mantle. This is a silicate rock. Most of the Earth is made out of the mantle. About 70% of the Earth is the mantle. This is inaccessible except by seismic waves, although once in a while a piece of the mantle gets shoved up on top of the crust and we can look at it. Then the part of the Earth that everybody's familiar with is the crust, and that's what we live on. That's where we get our resources. That's what we mine. But it's only a very thin scum on top of the mantle.
Even today, more than 4.5 billion years after the formation of the Earth, there are two layers of the planet that remain molten or partially molten. The uppermost mantle beneath the crust has now solidified, but a zone beneath it, several hundred kilometers thick, approaches the temperature of melting. This is where the lava in most oceanic volcanoes comes from. The outer part of the Earth's core is also still completely molten, but the inner core, although even hotter, remains solid. This is due to the fact that when rock melts, it expands. But at the center of the Earth, the the pressure of the 5,000 kilometers of overlying rock is so enormous that no expansion is possible. And as a result, the superheated iron cannot turn liquid. The great amount of heat still present in the Earth is demonstrated by active volcanoes. The volcanoes of today are an awesome spectacle. But more feverish convulsions affected this planet when the Earth was young.
In the present Earth, the amount of liquid rock is really quite small at any time. But in the early Earth, a big fraction of the volume would have been molten. So we imagine that the very earliest Earth had an extremely high level of volcanic activity. When this volcanic activity takes place, gases which are dissolved within the liquid rock are expelled, put into the Earth's atmosphere. And in this way, we can imagine that the early atmosphere of the Earth was built up by volcanic activity.
Our early atmosphere was something you and I would not want to breathe. Well, we wouldn't even today want to go breathe the air that comes, or the gases that come out of volcanoes. It's rich in sulfur, carbon monoxide, carbon dioxide, many of the same things that are emitted from exhaust pipes of cars are coming out of volcanoes. They did then, they do today. It's a very acidic and very toxic gas. So our early atmosphere was pretty hazardous.
Volcanic activity also released vast amounts of water vapor. Many geologists argue that this condensed to form the world's oceans. Recent work, however, suggests that factors other than volcanism may also have played a role.
Another very interesting possibility is that the water came in comets, in bodies that formed in the far reaches of the solar system and were scattered into Earth-crossing orbits. We now see, of course, comets that cross the Earth's orbit, like Halley's Comet, and very rarely objects like this even hit the present Earth. But in the early history of the solar system, these collisions would have been more frequent. And the amount of water on the Earth, although we might think of it as being large because we live on the surface of the Earth, is actually quite small compared to the total mass of the Earth. And so you don't need a very large number of comets to explain all of the water that we see in the Earth's oceans.
Earth's distance from the sun and the presence of an atmosphere which kept surface temperatures warm allowed water to collect in a liquid state, submerging the young planet's raw basaltic lowlands. No other planet combines all the factors required for the existence of a watery ocean. An ocean may also explain the presence of life on Earth, for liquid water is an essential ingredient of biological reactions. The oceans played a further role in nurturing life, however, for Earth's early atmosphere was probably full of deadly solar radiation. Water would have screened out such radiation, enabling the fragile process of life's origin and early development to take place.
The most significant difference between Earth and the other planets in our solar system is that Earth has the conditions to support life as we know it. The abundance of water on Earth was critical to the origin of life. Water also helped moderate the temperature of the planet's surface to a range which enabled life to evolve. Oxygen gas, however, was not part of this primitive atmosphere. It wasn't until the development of primitive algae, about 1.8 billion years ago, that free oxygen became an important part of the atmosphere of the Earth. This paved the way for development of more complex life forms.
Primitive blue-green algae, or cyanobacteria, survive by taking one of the most abundant gases released by volcanoes, carbon dioxide, and combining it with water in the presence of sunlight. The result is carbohydrates used for food and an important waste product called oxygen. So, through time, early life forms helped to change the carbon dioxide-rich atmosphere to one rich in oxygen, thus permitting the evolution of modern life. In addition to biological activity, another major difference between our planet and most other terrestrial bodies in the solar system is that the Earth still experiences a great deal of radioactive decay. Mercury, Mars and the Moon are essentially dead worlds, too cold inside to create new volcanoes or great crustal movement. It's largely due to internal radioactivity that the Earth is a geologically active planet.
Our Earth is alive, and I just don't mean biologically alive. It's physically alive. It has an internal heat engine that is fueled by radioactivity. Without that, there would be no volcanoes. Without that, there'd be no earthquakes. Without that, there would be no ocean, no atmosphere, no running water, and no biologic life.
The Earth is very hot inside and cool on the outside. This means that there is a large temperature difference. When you have a temperature difference like this, you can drive a heat engine. This engine is not too much different conceptually from an internal combustion engine or any other engine that operates with two different temperature reservoirs. In the case of the Earth, what happens is that that temperature difference is sufficiently large to drive convection, an overturning of the fluid within the Earth, rather similar to what happens when you heat a pot of soup, heat it from the bottom and produce convection currents within that fluid.
A similar cycling motion seems to occur within the Earth, but at a far slower pace, over tens or even hundreds of millions of years. Local concentrations of the Earth's heat cause some parts of the mantle to expand, become less dense, and float upwards as far as the Earth's outer skin will allow. The warmer rock then spreads out and gradually radiates its heat through the overlying blanket of more brittle crust. As it cools, the rock contracts, once again becoming dense enough for gravity to pull it back down into the mantle. This constant churning of material within the Earth eventually buckles and breaks the crust, producing earthquakes, volcanic activity, and majestic mountain ranges. In ancient Greece, a builder was called a tecton. Science has coined the term tectonic forces to describe the internal processes that move mountains and unleash earthquakes and volcanism. Our gradual understanding of these processes has led to the formulation of what is perhaps the most profound concept in geology.
From time to time, theories result from scientific inquiry that fundamentally alter our view of the world. These scientific revolutions are elegant in their simplicity and demonstrate new connections between phenomena that had once appeared unrelated. Some of the better-known examples include the theory describing the structure of the atom in chemistry, the theories of quantum mechanics and relativity in physics, and the discovery of genes and DNA in biology. Within the last few decades, the theory of plate tectonics has revolutionized our understanding of the Earth. The theory ties together a wide range of geologic phenomena and makes it abundantly clear that the Earth is indeed a vitally active planet.
The central idea of plate tectonics is simple. The Earth's crust and upper mantle are broken into about a dozen large, rigid plates, somewhat like segments of cracked shell on a hard-boiled egg. These gigantic slabs of rock slip and slide as they are carried about by the convection currents in the partially molten layer of the upper mantle. A similar pattern of crustal plate motion is sometimes observed on the surface of molten lava lakes. The cooled skin of lava across the lake is broken into plates by the turbulent liquid beneath.
The earliest Earth was vigorously convecting as it tried to get rid of heat. The surface of the Earth at that time would have had some stiffness to it because it was colder, but as time went on, that surface layer became thicker and still more stiff. We see this process even taking place today in lava lakes, for example, on the big island of Hawaii. The stiff surface layer of the Earth becomes so stiff that it breaks up into plates. And so we expect, as part of the convection process of the Earth, that the surface becomes a set of mobile plates which are able to be continually created and recycled within the Earth. And this process is now known as plate tectonics. In the earliest Earth, it must have had some similar behavior, perhaps more complicated, perhaps more dynamic, perhaps more plates, but the plate tectonic process that we now see as the guiding principle of so much of geologic evolution had its beginning right in the early history of Earth.
Although scientists sometimes disagree about the details of our planet's origins, there's little argument that Earth is unique in our solar system. The fantastic diversity of life, the abundance of water, and our oxygen-rich atmosphere are all the direct result of this planet's unusual history, a history of physical, chemical, and geological evolution, as well as the evolution of life. What's especially compelling is that this process of change is not just part of Earth's past. It continues without interruption. This restless planet, with its interplay of tectonic forces, is as turbulent and dynamic as ever.